This is practice problem 2. We are given a 2 by 2 matrix A, and we are given two eigenvectors of A. We are not told the eigenvalues, we are simply told the eigenvectors. Use this information to diagonalize A. To diagonalize A, remember, it must be P minus 1 A, P equals to D. So we need to find D. Well, we have already been given P, we have been given A. Do we need to perform P minus 1? That's one way we can do it, but we do it more simply by remembering that A times V1 is equals to lambda 1 times V1. A times V2 equals to lambda 2 times V2. We can quickly find what is lambda 1 and lambda 2, and we can put it in D, which is simply lambda 1, lambda 2, and 0 elsewhere. Okay, so that's the trick. So we compute AV1. We found that this is A, this is V1, giving us V1. Therefore, lambda 1 is equals to 1. AV2 is equals to, this is A, this is V2, this is lambda 2 V2, showing us that lambda 2 is equals to 3. And now we can just simply form the matrix D is equals to 1, 3, 0 everywhere else. Okay, so this trick bypassed the computation of P. This is simple. We can actually do it both ways, but this way is easier. Alright, let's have some sanity check. We have A here, and to get MATLAB to perform eigenvalue decomposition, we send A into EIG, the function, and expecting two matrices, P and D. P is the eigenvector, D is the eigenvalue, and what happened is that we can get MATLAB to compute. So here's the answer. So this is A, this is P, and this is D. So we see that we got D correct, 1 and 3. Now the eigenvectors are arranged this way. This is V1 corresponding to lambda 1. This is V2 corresponding to lambda 2. Now, if you want to be very sure that there is no mistake, what you might want to compare is that this should be exactly this guy, and the second, it should be this one. So how do we know we are correct? Well, let's examine V1. V1 is the direction 3, 1. So if you now look at MATLAB solution, this first element is 3 times the second element. What about V2? The first element is 2 times the size of the first element. So it's 2 times the size of the first element. What about all these negative signs and things like that? It doesn't matter. Remember that eigenvectors are pointing to one direction. Pointing to an opposite direction is a negative. Eigenvectors are along these whole directions. And what about why is MATLAB producing all these funny values that are not so nice? It is because the norm of these vectors is equals to 1. So MATLAB actually compute the eigenvectors and then normalize it. So that's why you can get all these funny floating point numbers. But when you compute the norm, it is 1. Okay, now the second thing we have always been telling you is that this is A equals to P minus 1 D. Sorry. We've been always telling you that this is the definition of similarity transform, implying that A equals to PD P minus 1. So I put D here, so I compute to make sure that I get the value. So this is P1, which is what is given to us. This is D1, and then we get the same value of A. Okay, so So you just use MATLAB to do this mechanical computation to see that your algebra is